It's Mr. Pope from Grammar School for Boys, and today in the Algebra Number Theory Session 3 we're going to be looking at some basic simultaneous equations and inequality stuff. So why is this important? Well, it's probably, along with basic algebra, indices, surds, that kind of thing, it's probably the most ubiquitous skill, not only in A-level maths but probably in your mathematical career, is being able to check when systems of equations, multiple things agree with each other. You never usually solve a problem that just depends on one thing. You're usually solving a series of problems that are all interlinked. And being able to verify that results are true, whether they're consistent and they give answers that make sense, not only work, but can be interpreted into something meaningful, is really one of the most powerful skills you can have as a mathematician. So, what is a simultaneous equation? Well, simultaneous just means happening at the same time. So if I've got a set of simultaneous equations, let's say I've got something nice and easy. Let's suppose I've got x plus y equals to 3. And let's say I've got x plus 2y equals to 4. Okay, not particularly exotic, but I want to define a few things first. For a start, these x and y's are unknowns and they're variables. Okay. The other thing is that we have two equations here, and the important thing to notice is here they are called, they are linearly independent. Okay, and a key concept in linear algebra is that you need the number of equations linearly independent, so let's just put Li for linear independent. The number of linearly independent equations needs to be greater than or equal to the number of variables in order for this to be solved or have a chance to be solved for. So what do I mean by that? Well, at the moment I've got two unknown variables, x and y, and I've got two equations here that are linearly independent. And by the way, what I mean by linearly independent is where one is not a multiple of the other. Okay, so what do I mean by that? Well, if I was to write 2x plus 2y equals to 6, then essentially that's just the same as this equation, but everything is doubled. So if I was just to write these two equations, although there'd be two equations in x and y, they are not linearly independent, i.e. one is just 2 times the other, or the other one is half of the other. And so therefore, essentially what's happening is we're not gaining any new information, and this problem can't be solved, or rather it doesn't have a unique solution. Okay, for a system of equations to have a unique solution, ideally, or to have a unique solution or a solution that exists necessarily, then you need a system of equations where the number of linearly independent equations is greater than the number of variables. Here, greater than or equal to. And here, there's two linearly independent equations here. There's two unknown variables, so this definitely has a solution. Another point is that these are actually linear equations, and the reason they're linear is because all the variables x and y have power or order 1. Okay, if they didn't have a power of 1, so say they had a power of a half, or power of 2, or power of 232 over 7, and so on, if it's not equal to 1, then we say these are non-linear equations. Okay, so actually what we've got here fully are two linear equations that are linearly independent and that have two unknown variables in. And because it satisfies that these two equations are linearly independent and that the number of linearly independent equations is greater than or equal to the number of variables, there must exist a solution. So, how do we solve for two linear equations or more? And by the way, this technique, let's just write linear equations. Well, there's two ways. We can either use substitution, which is a powerful technique, or we can use elimination. So in either case, if I was to use substitution, then what you do is you make one variable the subject. So for example, from the top row, x plus y equals 3 will become x equals 3 minus y. And then the next step is you substitute it into the other equation. And that's really important, okay? Because if you substitute into the first, you're not going to get anything new. Whereas now, if I know x is 3 minus y, then I've got 3 minus y, which is x, plus 2y equals 4. And notice how I use brackets there to denote that a substitution has taken place. If I simplify this out, I've got minus y here plus 2y, so that becomes 3 plus y equals 4. If I subtract 4 from both sides, y equals to 1. And now that I know y is 1, I can just go back to x. And because x is 3 minus y, x is 3 minus 1, so x is 2. Okay, that's fairly standard. For elimination, you look to either add or subtract equations to eliminate a variable after scaling. Okay, what does that mean? Well, look, if I look at the x's of both of these, they're both the same amount of x's. So if I subtract one row from the other, the x's will disappear. So if I do the bottom row minus the top, x minus x is nothing, 2y minus y is y, and 4 minus 3 is 1, so y would equal 1. And then I will substitute this value back in to either equation. And to be honest, you should substitute back into both just to do a thorough check. So if y equals 1, x plus 1 equals 3, which will give x equals 2. And y equals 1, x equals 2 is consistent across both ways. That's not really a problem. How do you solve simultaneous equations when one is linear and one is non-linear? So non-linear simultaneous equations. Well, there's various tricks. You can use substitution. That's always a good way. So, and that's just done by rearranging one equation into another. Another thing you can do is not only can you add, subtract, but you can also divide and multiply equations to eliminate. For example, if I had r sine theta equals to 2 and r cosine theta equals to 1, then if I divide both of these, then I'll have r sine theta over r cosine theta equals to 2 over 1. The r's cancel, sine over cosine equals tan of theta equals to 2. And now that's something you can solve in terms of theta. So don't be afraid that, well, you can add, subtract, multiply, divide, all the usual rules of algebra, so long as you're consistent. The other thing I wanted to talk about when it comes to simultaneous equations is something called extraneous solutions. Okay, and I've talked about this before, but extraneous. Let's spell that clearly. Extraneous solutions. What do they mean? Essentially, they are when the solution found isn't valid to the original problem. And what I mean by that is, suppose you have done some operation like you've squared both sides, or you've taken the inverse trigonometric function of both sides, and so on and so on. Or you've taken the square root of both sides, and you know. The point is, whenever you perform an arithmetic operator like that, especially a nonlinear one, which squaring, square rooting, and trigging and inverse trigging are, then you're essentially you're kind of deviating off a little bit, and you still have to be very careful in the back of your mind that what you're actually answering makes sense. I'm sure the typical example would be when you're taking logarithms. For example, if I was to solve x squared plus, I don't know, let's suppose I've got some logarithmic equation, and these are functions of x's, and let's suppose I work out x to be minus 2 and x to be 4. Well, if I substitute minus 2 into a logarithm, then you won't get a real answer. So you can't take the log of a negative number and expect to get a real output. You need the complex logarithm function for that. So if you're looking for a real valued function and you substitute in a negative number into the logarithm function, then it's just not going to work. But x equal to minus 2 and x equals 4 might have been the solution to a quadratic, let's say x squared minus 2x minus 8 equals 0, for example. That very well could have been the case. And it might have been after rearranging this logarithm thing that you get a quadratic in x, and it spits out that x can either be minus 2 and 4, and then you have to do the check to see that if minus 2 and 4 are actually valid solutions and not extraneous solutions. Okay. So, simultaneous equations wise, let's do a nonlinear one really quickly. Let's suppose, let's do it down here. Let's suppose I have got x squared plus y squared equals 169, and x plus y equals to, 17. Okay, clearly this one is the non-linear equation, and this one is the linear one, because all the powers of x's and y's are 1s. By the way, if you had x times y, that's not linear either, because you've got an x to the 1 times y to the 1. You can kind of think of that as they're adding together, so this is kind of like a weird squared function. It's not. You have to have your variables separate. You can't multiply them together or conjoin them in a way. Another way of thinking about linear functions would be, if you were to plot them, would they form a straight line graph? That's the true test of whether a function's linear or not. Does it form a straight line, whether in 2-dimensional space, 3-dimensional space, 4-dimensional space, and so on? Anyway, getting on to this, the first thing you do is you rearrange the linear equation. So let's make x equals 17 minus y. And then I'm going to substitute this back into over here to get 17 minus y all squared, because I've used brackets to denote substitution, plus y squared equals 169. 17 minus y squared. 17 times 17, I want to say, is 289. 7, 9, 4, 7 times 1, 7. Yep, 289. So it's 289 minus, and 17 times minus y and then doubled is 34y, plus a y squared plus another y squared equals 169. 289 minus 160, I believe that's going to be 120. I've got a 2y squared, I've got a minus 34y like that. I notice that all of the coefficients are even, so I can divide everything by 2 because 0 divided by 2 is still 0. So this becomes y squared minus 17y plus 60. And then I notice that what two numbers add to minus 17 and times to positive 60, that's going to be y minus 5 times by y minus 12. So y can either equal 5 or 12. And then I look at the linear equation up here that I made the substitution for, and x is just 17 minus y. So if y is 5, x is 17 minus 5, which is 12. And when y is 12, x is 17 minus 12, which is 5. So there's actually two solutions to this set of equations. The point x is 12, y is 5, and the point x is 5 and y is 12. Generally speaking, if the highest order power generally dictates at most how many solutions there are. So because the highest power of the nonlinear function was squared, that means at most there can only be two solutions. If it was cubed, then there might at most be 3, but there might be 2, there might be 1, there might be none. It just depends on the graph. If it was linear, then at most 1 might not have any solutions at all. Okay, so here's a nice little simultaneous equations question for you. Pause the video and give it a go yourself. Okay, so y equals x minus 2 is clearly the linear one, and this is clearly the non-linear. So standard technique, we're going to substitute the linear one into the non-linear one. So if y is x minus 2, then I've got x minus 2 squared plus an x squared equals 10. Expand the brackets quickly, we'll get an x squared minus 4x plus a 4, but I've already got an x squared there, so it's a 2x squared. There's a 10 there, so that's going to be 2x squared minus 4x. Subtract 10 from both sides is minus 6. Luckily, all these coefficients are even. I could factorise as it is, but I'd rather not. So x squared minus 2x minus 3 equals to 0, which looks like x minus 3 times by x plus 1 equals to 0, which is going to give either x equals 3 or x equals minus 1. And because we've got the original thing up here, y equals x minus 2, then 3 minus 2 means y equals 1. And when x is minus 1 minus another 2 means y equals negative 3. As a final check, we could substitute these things back into the original question. We might as well. Well, I used the first one to check what they were, so I know that's consistent. It's the second one I need to be careful of. So if I square each of these things, do they give them 10? Well, 3 squared plus 1 squared is 9 plus 1, which is 10, so that works. And minus 1 squared is positive 1, and minus 3 squared is positive 9. 1 plus 9 does equal 10. So yes, neither are extraneous solutions. This system of equations has a consistent pair of solutions, and that is x is 3, y is 1, and x is minus 1, y is minus 3. Okay, if you'd like to have a go at this question, it's a logarithms question. You may need to be careful with extraneous solutions, I don't know, but give it a go. Okay, so what have we got here? Well, log base 2 of xy squared equals 0 means 2 to the 0 equals this. That's how logs work. And 2 to the 0 is 1, so that's saying x times y squared equals to 1. Next up, 2 to the 3 is this thing, which means x squared y equals to 8. Okay, right, multiple things going on here. Now you could either substitute or you can do a bit of clever factorization, because I notice the right hand side here is actually y, lots of xy, and that equals to 1. And over here I've got 8 equals to x, lots of xy. And now if I divide one by the other, I get this one divided by this one gives x over y equals to, well, 8 divided by 1, which is 8. And if I times by y both sides, that means x equals to 8y. So now I can solve. I can substitute this thing into either of these equations originally. I'll substitute into the first one. If x is 8y, then 1 equals 8y times y squared, which is 8y cubed. If I divide by 8, then 1/8 equals to y cubed. If I cube root both sides, the cube root of 1/8 is 1/2. And if y equals a half, then x equals 8 times y, and a half times 8 is 4. So I'm just going to substitute both of these things back in and make sure I haven't made a mistake. So log base 2 of x, which is 4, times 1/2 squared. 1/2 squared is 4, so 4 times a quarter is 1. Does that equal to 0? Yes, because 2 to the 0 is 1, correct. Log base 2. X squared, which is 16, times by y, which is a half. 16 times half is 8. Does that equal to 3? 2 to the 3 is 8. Yes, that works. So there you go. X is 4 and y is 1/2. Are the only solutions to this. Cool. Only real solutions anyway. Okay, inequalities. So what is an inequality? Well, an equation would be something like this. 2x plus y is equal to 3. But an inequality would be where I've got something like 2x plus y is less than 3, for example, or less than or equal to. It just depends on the context. And the key point to this is inequalities denote regions or sets of numbers. So for example, if I'm trying to solve 2x plus 3 is less than or equal to 5, say, then I do this in the normal way. I subtract 3 from both sides to get 2, like so, and I can divide by 2 to get x is less than or equal to 1, which means on a number line, if this is 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, then I'll have a solid dot because it's a less than or equal to, and I want all the numbers to the left. If it was just strictly less than 1, so something like this, then instead of a solid dot, it would be a dot with a hole. Right, what else? Well, the other key thing to note is that inequalities behave like equal signs, but the only difference, except when multiplying or dividing by a negative number. That's such a key thing. Right? Inequalities behave like equal signs except when you're multiplying and dividing by negative numbers. So here's an example. 1, negative 1 is less than 2. That's totally fine. Everyone agrees with that. Now if I multiply by minus 1 from both sides, then this becomes positive 1, this becomes minus 2. Now this no longer makes sense. 1 is not less than minus 2. So to combat this, we need to flip the inequality sign. Similarly, multiplying and dividing by negative numbers flip them. But also another thing that happens is when we reciprocate. So here's an example of what I mean by there. Well, 2 is less than 3. I hope you agree. But if we take the reciprocal of both sides, and I've got 1/2 on the left-hand side and 1/3 on the right-hand side, well, clearly 1/2 is bigger than 1/3. Now, there's various other things you need to be careful of, like dealing with algebraic fractions, but we'll come to them in due course. Now, linear inequalities, you can kind of, these are linear, right? Because 2x plus 3 is a linear function of x. It will produce a straight line. However, when we're dealing with non-linear inequalities, you have to be really careful. And essentially the main thing you need to do is plot or sketch to find critical points. And I'll do an example just to make sure you get what I mean. Okay, so let's take 3x squared minus 8x minus 3 is less than 0. Okay, so what I'm going to do is I'm going to take this quadratic function and I'm going to try and solve for it when it equals to 0. So luckily for me, I think that's going to be 3x x. Now I want to say this is a 3, this is a 1, this becomes a plus 1, that's a minus 3. Yep, so if I consider this factorisation first, which does equal the top bit, then either x equals minus a third or x equals positive 3. So if I was to plot y equals 3x squared minus 8x minus 3, then it would cross the x-axis at 3, at minus a third, and the y-axis at minus 3. So it looks something like this. Now, I want to know where this curve, this 3x squared minus 8x minus 3, has an output y that is less than 0. Well, that's these points here, right? All these values have y coordinates less than 0. And they correspond to this part on the x line, i.e. when x is between minus a third and 3. So that would be my answer. If it was 3x squared minus 8x minus 3 is less than or equal to 0, then I would change it to this. And technically, if it was less than or equal to 0, then I don't actually have a parabola like that. I actually have a dotted parabola like this because I'm not actually including the parabola itself. Okay, other thing to note is suppose it was the other way around and it was actually greater than 0, then what would I do? Well, let's think about it. In actual fact, let's have this here. Let's copy it. So what would happen when it's bigger than 0? So over here. Okay, so what would change? Well, not a lot really, except this answer is clearly wrong. But we do the same steps. We'd factorise it or try and plot it, consider the function where the critical values are. In this case, minus the third and 3. And this time I want to know whether the function is greater than 0. Well, clearly this fork and this fork are where the parabola has a y-coordinate greater than 0. And each of those points, if you drop them down to the x-axis, they correspond to x values that are less than minus a third, but greater than 3. Now here's the bit that people mess up. There are two regions here. Think about it. There's one on the left-hand side, there's one on the right-hand side. So we need to have two inequalities, i.e. x is less than minus a third and x is greater than 3. Now, if you want to be really technical about it, and we've done Venn diagrams now, you'll notice that this set, x is greater than 3, and this set, x is less than minus 3, I want the union of this set, i.e. in set notation form, I want the total coverage of these two sets, i.e. x maps onto these two sets. X is less than minus a third and x is greater than 3. Okay, you might want to represent this down on a number line. For example, here it is, 0, 1, 2, 3, minus 1, minus 2, minus 3, greater than the third is an empty dot onwards, less than minus a third, it's above the third and it's back like that. If this was greater than or equal to, then how would that change my answer? Well, this would be greater than or equal to 3. This would be less than or equal to minus a third. The parabola would be a solid red thingy, and these dots would be fully shaded in, like so. Okay. Generally speaking, if you want to check an inequality is true, I would substitute in some values just to watertight test it. Does it actually hold up? Okay. Now there's various inequalities, not just quadratic ones, that you have to solve for. And generally speaking, it's always a good idea to just draw a sketch or plug in some values and see what's going on. So let's have a look at a couple. So pause the video, give it a go yourself. Okay, find the set of values for which this is true. Well, if I expand it, I get 3x minus 6 is less than 8 minus 2x. If I add 2x to both sides, this is 5x. If I add 6 to both sides, this is 14. So clearly x is less than 14 over 5. If I look at this one, it's for part B, it's already factorised for me. So the critical values are x is 7 over 2 and x equals to minus 1. It's a positive quadratic, so it's going to be a U-shaped parabola looking like this, where it's going to cross the x-axis at minus 1 and at 7 over 2, which is 3.5. It's going to have a y-coordinate of minus 7. So it's going to be a U-shaped parabola looking like that. And I want it less than 0, so all this stuff, which is between minus 1 and 7 over 2, so the answer is x is less than 7 over 2, but greater than minus 1. And then I want to know when both of them are true. So let's just draw a number line and see what happens. So here's 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, and so on. So the top one, x is less than 14 over 5. Well, 14 over 5 is just under 3. So there's 14 over 5. And I want everything less than it. And now the second one, when x is greater than minus 1, so there's minus 1, and less than 7 over 2, which is 3.5, so 1, 2, 3.5, so 7 over 2 is out here somewhere, so it's trapped between these two things. Now, do you spot that the only region where both of them are true is between here and here? Any x value in here will satisfy both. So the answer clearly is going to be x is trapped between 14 over 5 at the top end and minus 1 at the bottom end. Being able to check when inequalities are valid for multiple filters is quite important. Okay, now this question's quite a toughie. It was taken from a physics aptitude test for Oxford. If you want lots of time, I suggest give yourselves 10-15 minutes or so. But pause the video now and give it a go. Okay, so sketch the regions in the xy plane defined by these inequalities. So 1 is less than xy is less than 2. Right, let's deal with this one first. So what does that mean? Well, if 1 is less than xy is less than 2, the trick is to do a pair at a time, i.e. consider 1 is less than xy, and then consider secondly when xy is less than 2. Okay, so how about we just, just do a little sketch, sub some values in, see what's going on. Well, when x times y is 1, well, there's lots of things that could be. That could be when x is 1, y is 1. There it is. But I want it to be greater than 1. Okay. Let's consider all the points when xy equals to 1. Well, when x is a half, y is 2 now. When x is 2, y is a half. And you can see it's going to have this sloping pattern here. And this is called a hyperbola. And by the way, if x times y equals 1, we could have had minus 1 and minus 1, which is down here. And we could have had x is minus a half and y equals minus 2. And we could have had x is minus 2 and y is minus a half. And in actual fact, we're going to get a symmetrical shape in quadrant 3. By the way, this is quadrant 1 in the top right, quadrant 2 in the top left, quadrant 3 in the bottom left, and quadrant 4 in the bottom right. Okay, so let's take another one. X times y is less than 2. Well, same deal. Let's consider x times y equals to 2. So when x is 1, y is 2, so it's up there. When x is a half, y is 4, so it's further up. When x is 2, y is 1, so it's parallel there. So it looks like we've got a similar sloping shape like this, and x equals to y. X times y equals to 2 is always going to be above that. And by symmetry, it's going to be a similar shape just below it down here, because minus 1 times by minus 2 would be over here somewhere, and so on. Now, what is this thing saying? I want xy is between 1 and 2. So that region we're interested in is going to be this gap between the two curves. Okay, that's totally fine. And technically, because it's a strict inequality, these should be dashed. So if I was to do this again, these are dashed, and these are dashed. Okay, so for all intents and purposes, I want the bits in between those two little rainbow type things, so that one's done. Now what about a half equals y over x and is less than 2? Well, same deal here. Let's consider a half is less than y over x, and let's consider y over x is less than 2. Now this one actually is a lot easier to deal with, because if I multiply both sides by x, well, what's going to happen? Well, let's think about it. When x is positive, then it becomes y is greater than a half x. And when x is negative, then I flip the inequality, so y is less than a half x. Now that's really important. This inequality is going to behave like a half x. And what is a half x? A half x is a line with slope a half. This is y equals a half x. By symmetry, I can do the thing over here. If x was positive, then y is less than 2x. And if x is negative, then y is greater than 2x. So actually, we're going to have a gradient 2 line, which is going to look like this going through the origin. Okay. So what's happening here? When x is positive, we're saying that the y values are greater than the half line, so above the lower one, so above this one, but they're lower than over 2, so it's going to be there. So actually, where does it all make sense? Well, below the upper line, above the lower line, and in the wedge, means we're actually going to shade this weird curvy rectangle bit. In that region, both of them are satisfied. Now if we look when x is negative, y is less than the lower slope, so it's below this line, and y is greater than 2 over x, y is greater than 2x, so it's above this line. So remember, it's above one line, below the other, and it's in the band. So by symmetry, we're going to get this curvy rectangular shape as well. So in actual fact, the inequality looks like this. It's a region of points. There's lots of x's and y's in there that satisfy this. And they kind of look like weird curvy rectangles that are opposite each other in quadrants 1 and 3. Yeah, that's it. Did you get that? You can also use desmos.com or Wolfram Alpha to plot these two things to convince yourself that's the right answer. Okay, graphical methods and applications. When it comes to simultaneous equations and inequalities, being able to sketch them and graphically interpret what's going on, I can't stress the importance of being able to do that kind of stuff. For example, if I've got a curve going like that, and let's say this is y is f of x, and I've got another curve, say it's doing something like that, where that's y equals g of x, then if I solve simultaneously g of x equaling to f of x, then the solution to this, where they equal to each other, will be where the two graphs have the same output, and that's going to be the point of intersection. So by solving this, you find points of intersection. Conversely, if there are no solutions to when you solve simultaneously, i.e. f of x equal to g of x, then that means there's no intersection points. The graphs don't actually intersect. And that's an incredibly powerful thing you're trying to prove, especially if you want to prove that one function is always bigger than the other. Because if one function is bigger than the other in a certain interval and they never intersect, then you can actually prove that one function is always bigger than the other one across the whole thing. Because, you know, if I've got that one function is kind of floating around here, and I've got another function is floating around here, and you say that in this and this interval that the red one is always bigger than the purple one, and then you prove later on that there is no intersection points, then it must be the case the red one is always floating above the purple curve. And so there's just various applications, and you just have to take it case by case and use all the skills we've gained so far. But the point is, solving simultaneous equations means that you're finding intersection points. And when we do vectors, there's not just intersection points, there might be intersection lines when we're dealing with 3 dimensions. For example, I might have a plane, there's my sheet of paper, and I might have another plane sticking at it at a funny angle, like so. And it might be where the 2 pieces of paper cross each other, they form a line. Okay, if one, well, let's say, let's try and make it look 3D. Let's say one curves like that, and then, no. So, and then indicates it's going behind. And then they'd intersect at a line, for example, like that. You know, it just depends. It depends on the object you're talking about, but being able to solve things graphically is incredibly useful. Okay, so enough clacking. Bit of simultaneous equations, then integrations going on here. So if you want to solve, pause the video, give it a go. Otherwise I'm going to do it now. So the figure above shows the graph curves with equations so and so. The finite region R is bounded by the 2 curves in the first quadrant, and it is shown shaded in the above figure. Determine the exact value of R. Well, we need to find the points of intersection there and there. So we need to set x squared minus 1, which is the first value, equal to 9 lots of 1 minus 1 over x squared. Right, so first thing, if I look at this, this is actually going to be x squared minus 1 over x squared, if I get it over a common denominator. And if I multiply both sides by x squared, I'm going to get x to the 4 minus x squared equals 9 lots of x squared minus 1, which is going to be x to the 4 minus x squared equals 9x squared minus 9. And if I subtract 9x squared and add 9 to both sides, I get x to the 4 minus 10x squared plus 9 equals to 0. And this looks horrible, but actually, in fact, this is a quadratic in disguise where you let a equal to x squared, and then this is going to be a squared minus 10a plus 9 equals to 0, which is a minus 9 times by a minus 1. And that's going to give that a equals 9 and a equals 1. And since a is x squared, that means x squared equals 9 or x squared equals 1. So that means x could be the positive or negative square root of 9, which is 3, or x could be the positive or negative square root of 1, which is 1, plus or minus 1. Now, clearly, in the context of the question, this point here must be when x equals 1, because it's positive and it's the lower of the 2 solutions. And because this is the bigger positive solution. This must be x equals positive 3. Now there's probably other solutions in the negative x values where this curve intersects each other, but we're not particularly interested in that. Now, going back to integration, this is what we need to do. To find the area of this curve, we will integrate between the top limit, which is 3, the bottom limit is 1. That's the whole point of doing it by simultaneous equations. And then it will be the top function in this interval, which was the 9 lots of 1 minus x squared. It's x squared minus 1 over x. Well, let's just leave it as that. That's 1 minus 1 over x squared. And then minus the bottom function, which is x squared minus 1 dx. Okay, so let's tidy this up first. So it's the integral 1 of 9 minus 9 of 1 over x squared is x to the minus 2 minus the x squared minus the 1 dx. Okay, so when we integrate this, this is going to be the integral evaluated between, well, 9 minus 1 is 8, so 8 becomes 8x, add 1 to the power divided by the new power. Add 1 to the power, that becomes x to the minus 1, divide by minus 1, minus 9 divided by minus 1 becomes plus 9, and then minus x squared, add 1 to the power, so it's cubed, divide by the new power, so it's minus x cubed over 3. I could put the plus c, the constant of integration, but it's just going to be subtracted out, and this is evaluated between 3 and 1. Okay, so brackets, brackets, minus brackets, brackets. This is when I sub in x is 3. This is when I sub in x is 1. When x is 3, I've got 8 times 3, which is 24, plus 9 times 1 over 3. That's what x to the minus 1 is. So 9 over 3 is 3. Minus 3 cubed over 3. Well, 3 cubed is 27 over 3 is 9, so that becomes minus 9. Then when x is 1, I've got 8 times 1, which is 8, plus 9 over 1, which is 9, minus 1 cubed over 3, which is minus a third. Okay, 24 minus 9 is 15, plus 3 is 18, minus 8 plus 9 is 17, and minus a third. 3 17s are 51, so 51 thirds minus 1 third is 50 thirds. Oh, is that right? Doesn't seem right to me. What's going on here? That's interesting. 24. Yeah, 8 plus 9 is 17. 17 times 3 is definitely 51. Okay, so 18 minus 50 over 3 is actually 48. Oh, geez, silly boy. That's 54 over 3. So 54 over 3 minus 50 over 3 is 4 thirds. So the answer is 4 thirds. It's 4 thirds units squared. Yeah. Yeah, tricky. Your calculator can integrate those things for you, I'm sure. But that's how you do it without a calculator. Okay, last question. Pause the video if you want to give it a go yourself. Okay, the diagram above shows the curve with y squared equals 4 lots of x minus 2 and the line with the equation 2x minus 3y equals 12. The curve crosses the x-axis at the point A and the line intersects the curve P and Q. Write down the coordinates of A. Well, if it crosses the x-axis, that means y is 0. So that means I have to solve 0 equals 4 lots of x minus 2, and that's clearly when x is 2. So this is 2, 0. B, find using algebra the points P and Q. Well, I need to solve simultaneously. So what I'm probably going to do is I'm going to make the y the subject here. Yeah, so this becomes 2x minus 12 equals 3y. So y equals 1/3 of 2x minus 12. And then when I substitute that into the original thing, then I'm going to have 1/3 squared, which is 1/9, times by 2x minus 12 all squared equals to 4 lots of x minus 2. If I times both sides by 9, then I'm going to get 2x minus 12 squared equals to 36 lots of x minus 2. Now, here's a sneaky trick. 2x minus 12 is the same as 2 lots of x minus 6. And if that's still squared, I'll take the 2 out square, which is 4. So actually, it's x minus 6 squared times by 4 equals 36 lots of x minus 2. I can divide by 4 both sides. So actually, this is a 9. And x minus 6 all squared is x squared minus 12x plus 36. This is 9x minus 18. If I subtract 9 from both sides, I get x squared minus 21x. If I add 18 to both sides, that's 54, isn't it? Okay. 54. Well, how do I get 54? Does this factorize? Well, 54 is 2 times 27. Or I could divide that by 3 to make that a 9, that's 6. Could make that a 3 and 18. So it's minus 3 and minus 18. So x is x minus 3 times x minus 18. So either x equals 3 or x equals 18. And then the y values, well, I've got the choice. I can sub them into either. I'm probably going to substitute in to the linear one. And I know that 2x minus 12, and then a third of that is y from up here. So 2 lots of 3 is 6. 6 minus 12 is minus 6. Minus 6 divided by 3 is minus 2. So that's one of them. When x is 18, 2 lots of 18 is 36. 36 minus 12 is 24. 24 divided by 3 means y is 8. So the coordinates of P is the one to the left, which is 3 minus 2, and the coordinates of Q is 18, 8. Show that the angle PAQ is a right angle. Okay, that's fairly straightforward. So I want the gradient from P to Q. So it's going to be PAQ. I want PAQ, so I want that angle to be 90. Okay, so I need P to A, or A to P, sorry. So A to P, so it's the change in Y. So the Y so it's the change in Y of P minus the change in Y of A over the change in X of P minus the change in X of A. So P's Y is minus 2. Minus A's y, which is 0, over P's x, which is 3, minus A's x, which is 2, minus 2 on the top. 3 minus 2 is 1, so that gradient is negative 2. To show this perpendicular, I have to show now that the gradient of A to Q is the negative reciprocal of 2, which is a half. So let's do the business. So Q's y coordinate is A, minus A's y coordinate of 0, over Q's x coordinate, which is 18, minus A's x coordinate, which is 2. So that's 8 minus 0. 18 minus 2 is 16. 8 over 16 is a half. And indeed, they're negative reciprocals of each other. So they are actually indeed perpendicular. Anyway, guys, I've left a load of exercises for you to work through. If your algebra is pretty decent, you should be able to get this. It's not particularly difficult. You just have to substitute things together and take your time. Okay, no worries. Peace.